For this question, we're going to use the first and second derivative tests to determine the local maximum and minimum values of a function f. The particular function being f of x equals 7 plus 6x squared minus 4x cubed. So I think the first thing to think about here is what is a local maximum and a local minimum? We can think of a local maximum as a point on our function where right before the maximum, our function height is increasing, and right after the maximum, it's decreasing, right? It's a peak. And the minimum is kind of the opposite, right? It's right before our minimum, we would have a decreasing height to our function. And then directly after the minimum, we have an increasing height to our function. I plugged in the, this particular graph for just a visual example here. We can see this line represents that function, 7 plus 6x squared minus 4x cubed. So, even without using our first and second derivative tests, we can see pretty well that we're going to have a maximum here where x equals 1, and we're going to have a minimum here when x equals 0. So as we think about this one, it's all good if we can generate this image and see. It becomes just by visual inspection, we can see the max and the min. But let's use our derivatives here to make a little more sense of it. So what is the derivative, right? The derivative of a function shows the rate of change of that function. So if the derivative is positive, we would expect the function to be increasing. Right? If the derivative is negative, we would expect the function to be decreasing. So we can use that concept to say, well, if the derivative changes from positive to negative, then we know that there must have been some peak, right, where it was increasing, and then it hit a peak, and then it started to decrease, right? There's that shift from the positive derivative to the negative derivative. Similarly, we can think about the minimum in this way, right? We can say, if the derivative of the function went from decreasing or went from negative to positive, then we know that the function itself must have gone from decreasing to increasing, right? So there must have been some sort of low point, which we would call our local minimum. So with those concepts in mind, we can take the derivative of our function here. So we have f of x equals 7 plus 6x squared minus 4x to the power of 3. So let's see, if we say, let's take our derivative. So we have f prime of x, right? So as we're taking the derivative of this, we're just going to take the derivative of each of these parts separately. So the derivative of 7 is just going to be 0. The derivative of 6x squared, well, we use sort of our power rule there, right? We see, okay, this would be the same as saying the derivative of 6x squared would just be 12x, essentially, right? We're saying 6 times 2 times x to the 1. And then we have the derivative of our minus 4x cubed. That would become minus 12x squared, right? Again, we're just using that power rule. So here we go. We've found the derivative of f of x. So now, if we're trying to find our local min and max based on this derivative, we could say, well, let's just set the derivative equal to 0. So our derivative is 0. And we're going to see at what points does x, what value of x would result in a derivative equal to 0, right? That will show us where the peaks and the low points are on our function. So if we say 0 equals 12x minus 12x squared, well, we could maybe simplify this a little bit and think of it as 0 equals 12x times, I suppose, 1 minus x, right? So we can see from here, it's like, oh, okay, so if x was 0, then we would have 12 times 0, times 1 minus 0, that would equal 0. If x was positive 1, then we would have 12 times 1 minus 1, so 12 times 0, 0. So x could be two different things that would result in this being 0. It could be 0 or positive 1. And we can see that here, right? So this is good. That's what we expected because we have a low point when x is 0 and a high point here when x is 1. So as we're thinking about this, we'd say, all right, so x could be 0, x could be 1. So a couple ways we could think about this. If we're trying to figure out, well, is it a maximum or a minimum, right? We can see on the graph when it's a max or min. But this here, this little analysis here of our first derivative test does not necessarily tell us if it's a maximum or minimum. There's a couple ways you could do it. You could plug in values near 0 and 1. For example, you could maybe plug in f prime of 0.5 and f prime of negative 0.5, and you would see that when we have the negative 0.5 in here, we're going to have a negative derivative, so we know it's decreasing before our 0, and then for our f of 0.5, we would get a positive answer. We'd see it's increasing afterwards. That's one way to do it, but if we want to focus on the second derivative test for this particular one, let's go into that, right? So the second derivative, that is typically, we're going to associate that with the concavity of our function. So first, let's solve and see, what is f double prime of x, right? So the derivative of the derivative, well, let's see here. The derivative of 12x is just going to be 12. And the derivative of negative 12x squared, well, that's going to be negative 24x, right? So what this tells us then is that we could plug in our values 0 and 1 into our f double prime of x, and it would tell us what is the concavity at that low or high point, right? We know that the rate of change, switched from positive to negative or negative to positive at 0 and 1, but we don't know, if it did go from positive to negative or negative to positive necessarily. We need to, or one way we can investigate that is thinking about what is the concavity at that point, right? So if we try out f double prime of 0, for example, f double prime of 0, this is just 12, right? So we have a positive second derivative when x equals 0. So what does that tell us? That tells us that we are going to be concave up when x equals 0, right? It's essentially showing us that we have this concavity that goes up like this when x equals 0. So if we're concave up at that sort of low or high point, that max or the min, if it's concave up, it tells us, well, it must be a minimum, right? We must have gone down and then shot back up. So that gives us our minimum. And then in contrast, what if we try when x equals 1? We know that's another one of our terms, or another one of our sort of max or min points, right? So f double prime of 1, well, that's going to be equal to 12 minus 24, which just gives us minus 12. So minus 12, clearly negative. That implies that when x equals 1, the concavity of our function f is going to be concave down. So that is to say that if we know that when x is positive 1, we know that the function itself is going to be sort of concave down in shape. That tells us that if we're confident that when x is 1, we have a max or min, it must be a maximum because we know that it's concave down. So we must have increased and then reached some sort of maximum, some sort of peak, and then it sort of curled back around and decreased again, right? So that would be the way that we could say then. So when x equals positive 1, we're going to have a local max in this case. And when x equals 0, we're going to have a local minimum.